The journey of hydrogen as a scientific and industrial marvel began in 1766 when Henry Cavendish first produced what he termed inflammable air through metal acid reactions. This early work laid the foundation for understanding hydrogen's properties as Cavendish meticulously measured its density. By 1783, Antoine Lavoisier had furthered this understanding by naming the element hydrogen and demonstrating that its combustion results in water, a pivotal discovery that linked hydrogen to the fundamental processes of chemistry. The turn of the 19th century saw further advancements with the work of Nicholson and Carlisle, who conducted the first electrolysis of water, successfully releasing hydrogen and oxygen. This experiment not only confirmed the composition of water, but also opened new avenues for chemical research. In the early 1800s, Michael Faraday's investigations into hydrogen's role in electrochemistry and electrical conduction provided deeper insights into its behavior in various chemical reactions. By the mid 19th century, hydrogen production had scaled significantly through methods such as coal gasification and steam reforming, marking the beginning of its industrial applications. The potential of hydrogen as a lifting gas was first realized in 1783 when Jacques Charles and the Robert brothers launched the inaugural hydrogen-filled balloon. Throughout the 19th century, hydrogen became the preferred choice for balloons and rigid airships due to its superior lifting properties. However, this preference came with inherent risks, as tragically demonstrated by the Hindenburg disaster on May 6, 1937. The airship, which used hydrogen to compensate for helium shortages, ignited catastrophically at Lakehurst, New Jersey. This disaster marked a turning point in airship design, leading to a shift towards helium, a non-flammable alternative, effectively ending the use of hydrogen in passenger aviation. The invention of the hydrogen-oxygen fuel cell by William Robert Grove in 1839, known as the gas voltaic battery, was a significant milestone in the development of hydrogen technology. This early fuel cell laid the groundwork for future innovations. In the 1870s, Ludwig Mohn and Charles Langer improved the efficiency of these cells by enhancing alkaline electrolytes. By 1893, Thomas Threlfall and his contemporaries had deepened the understanding of hydrogen-oxygen electrochemistry, paving the way for practical applications. In 1932, Francis Thomas Bacon advanced the field by creating a fuel cell with higher power density, which would later influence the direction of fuel cell research in the 1940s. This period saw a shift towards developing portable and stationary applications, setting the stage for the use of fuel cells in space exploration. NASA's pioneering use of hydrogen in space missions began in 1959 with the Centaur upper stage, the first rocket stage powered by liquid hydrogen (LH2) and liquid oxygen (LOX). This innovation demonstrated the potential of cryogenic hydrogen propulsion. By 1962, the Saturn I's S4 stage had further showcased the capabilities of this technology. The period from 1968 to 1972 saw the Saturn V's S2 and S4B stages enable the Apollo lunar missions, utilizing LH2 LOX to achieve unprecedented feats in space exploration. From 1981 to 2011, the Space Shuttle's RS-25 main engines, operating on LH2 LOX, facilitated reusable spaceflight, marking a significant advancement in space technology. In the 2020s, NASA's Artemis program continues to advance LH2 LOX engine technology for lunar and deep space missions, underscoring hydrogen's critical role in the future of space exploration. The commercial application of hydrogen fuel cells began with the 1966 GM Electrovan, the first fuel cell vehicle. Based on a GMC Handy Van, it utilized a NASA-derived hydrogen-oxygen fuel system. Despite its innovative design, the Electrovan was a one-off prototype, hindered by the high cost of platinum and logistical challenges in refueling. In 2002, Toyota and Honda introduced the FCHV and FCX, respectively, among the first government-certified leased fuel cell vehicles in Japan and the US. The 2014 launch of the Toyota Mirai marked a significant milestone as the world's first mass-produced fuel cell sedan, with over 31,000 units sold globally by 2020. Despite its commercial success, infrastructure challenges persist. From 2018 to 2024, the focus shifted to hydrogen-powered buses and trucks, with models like the Toyota Sora and Hyundai Xciant leading the way. However, by 2025, Stellantis announced the discontinuation of its hydrogen fuel cell program, citing limited infrastructure, high costs, and lack of demand. This decision highlights the ongoing challenges in achieving widespread adoption of hydrogen technology in the automotive sector. Hydrogen fuel cell technology has evolved significantly since the 1800s, emerging as a niche yet impactful solution in mobility. Early breakthroughs, such as the electrovan and the invention of the fuel cell, laid the critical groundwork for future developments. NASA's successful use of hydrogen in space missions demonstrated its viability and performance advantages. Commercial adoption has increasingly focused on heavy-duty transport, while passenger fuel cell electric vehicles, FCEVs, remain constrained by infrastructure limitations. The decision by Stellantis to exit the hydrogen market underscores the persistent hesitancy within the industry, suggesting that hydrogen's future may be more promising in commercial fleets rather than mass-market passenger cars.